Hello, everybody. Welcome back to EM378SI Online. Today we got a problem to go through, problem 762, and it's on the modeling and similitude that we've been working on for the past week. So just a little bit more practice with that. We'll get into it. All right. So an incompressible fluid oscillates harmonically with a velocity and a frequency of 10 radians per second in a 4-inch diameter pipe. A 1/4 scale model is to be used to determine the pressure difference per unit length, or delta PL, at any instant along the pipe. Assume delta PL is a function of these variables. D is diameter of the pipe, omega is frequency, T is time, mu is fluid velocity, rho is fluid density. All right. Determine the similarity requirements for the model and the predicted equation for delta PL. And if the same fluid is used in the model and the prototype, what frequency should the model operate at? All right. So they already have our variable relationship written up here. So we're just going to start right in with our chart of the variables and their respective dimensions. Alrighty. So change in pressure, that's going to be FL to the negative 3, D is L, velocity L to the negative 1, omega is time to the negative 1, time is just time, mu is FL to the negative 2T, and density is force length negative fourth time squared. All right, and we can look at this, and what we're going to do, so we know that, well, for one, K is 7, R is 3, so we're going to need 4 pi terms. All right, so that's quite a few, but here's what we can do. We know that we can kind of tell a few of them by inspection, right? So the first one that we can tell by inspection is this relationship between omega and time. If you just multiply these two together, that's going to be a dimensionless variable, right? Time to the negative 1 times time is just going to be t to the 0, which is just 1. So dimensionless. So we got that one going for us. And then also, one thing that you'll see a lot more of, again, that we're talking about is the Reynolds number. And this is going to come up a lot, not only in this week, but also once we get into pipe flow and stuff like that. So Reynolds number is a dimensionless variable with rho v d over mu. And what we notice is that we have rho, v, d, and mu, right? So we can say the Reynolds number is also going to be one of our pi terms. So already we found 2 pi terms just by inspection, and then the other 2 you can find just by the process that we've seen in other videos. We won't spend time on that here just so we can get into the rest of the problem, stuff that you maybe haven't seen before. All right, so one of those pi terms that you'll come up with, d times delta PL over rho v naught squared. So that's one of our pi terms. That's a function of our other 3 pi terms, v0 t over d, omega t, and then rho v naught d over mu. So we saw this relationship by inspection, and then this again is our Reynolds number, right? Reynolds number is our 4th pi term. Alrighty, so part A, determine the similarity requirements for the model and the prediction equation for delta PL. So that sounds kind of weird, right? I'm not sure if we've gone over similarity requirements or called it a prediction equation just yet. But all that means is that we know that we're going to take one of the pi terms that includes the variable that we're looking at, so in this case delta PL, and its let's see, its prediction equation is the term that they're using, is going to be just delta PL rho V naught squared is the same as, so this would be our prototype, and then in our model. And that's all there is to it. This is prediction equation for delta PL. All right, so delta PL was one of our non-repeating variables, and so we can set up a prediction equation for it using just one of these pi terms. Alrighty, and part B, we'll solve that one next. If the same fluid is used in the model and the prototype, at what frequency should the model operate? So, same fluid, and what same fluid tells us is that the rho of the prototype is going to be rho of the model, and viscosity of the prototype is going to be the same as the viscosity in the model. So those two, we'll see how that works itself out. And then also what we're looking for eventually is the frequency of the model, right? So omega m, what is it? Well, we'll find out. So looking at our pi terms that we have up here, the relationship that we want to look at is this one here, the one that involves our omega. So we know that omega model, t model, then we see it as omega times time of our prototype. Eventually we know omega model, just moving the variables around, is omega t over our model. And we know the omega of our prototype, right? That's given up here. That's 10 radians per second. The problem is we don't know this ratio here of t over t of the model. So we look at our other relationship that involves t, right, to try and find a relationship between t and t model. So we'll look at this second pi term here. So VO t over d, VO model t over d model, or t model, sorry. All right, moving our variables around a little bit. With this, we get t over t model is d VOM over VODM. Cool. So you can say to yourself that also doesn't really help us because we also need to find a relationship between VOM and VO. Well, we can do that with our Reynolds number up here. And we know the relationship between the diameter and the diameter, and the diameter of our prototype and the diameter of our model. Right, that's given in this relationship here, a 1/4 scale model. So we know that, let's see, where am I looking? Right, okay, sorry, I was lost in my notes a little bit. So we know that this is going to be, one sec, let me backtrack. We'll come back to this. Before we do that, from Reynolds similarity, rho VO d over mu, rho m VO m dm over mu m. All right. So since we have this relationship here, we're using the same fluid. These are going to cancel out, and then we can get our relationship between VOM and DM. And what we find out is that the velocity in our model is the velocity in the prototype, the same way that the diameter in the prototype is to the diameter in the model. Sorry, that's an M. So this, come back up here, we get that our T over Tm relationship is just D over dm squared. So then we know the relationship between D over dm is 4, right? So that is 4 squared, right? We get that from this relationship here. Our 1/4 scale model means that D over D model is 1/2. All right, so 4 squared, 16. And then we just plug this back into here, this relationship for the ratio of times, and then we can multiply by the omega that we're given in the problem statement of 10 radians per second. So we get omega of the model is the same as omega times 16, 10 times 16, 160 radians per second. Neat. So that's that problem there. I will quick go over some just business stuff. So SI stuff going forward. One thing that I'm going to continually encourage is webex, right? That's Mondays from 6 to 7, Tuesdays from 6 to 7, and then Thursdays from 5 to 6. This is Iowa time. And one thing that I'll be doing to encourage WebEx is half of problems uploaded to the channel. And then the other half of problems or content that we do through WebEx. So this is just to encourage you guys to come, because I know even if you don't think it now, you're going to have questions as we go through later stuff. And so just getting into the habit of showing up to WebEx, being able to have questions to ask, and then I'll be able to help out with that. But it's not as efficient to do that through this channel here. So half of the problems can be here, just in case if you can't make it to those WebEx meetings. I don't want to punish you for not being able to make it to that. And then half of the problems we'll do in WebEx. I know that policy keeps changing a little bit, but I'm just trying to figure out the best way to get attendance and people asking questions through WebEx while also giving you guys the content that you are paying for. Alrighty. And with that, here's a smiley face. Hope you guys are doing great with this online stuff. Let me know in the comments if there's any questions that you have or suggestions, anything like that. Alrighty. Thanks for watching. I will see you guys tomorrow in WebEx. And if not, make sure you're watching the videos and keeping up with the content here in Fluid Mechanics. Have a good one.